When we talk about AI, we usually picture all this complicated code, right? These super abstract algorithms. But what if I told you the real magic, the real power, isn't just in the code? It's in this elegant, hidden geometry. Today, we're going to pull back the curtain and see how linear algebra is the true blueprint for how AI thinks. So, have you ever really stopped to wonder, how does a machine actually think or learn? We imagine these crazy tangled webs of code. But the real answer? It's way more visual, more spatial than you'd ever guess. Because at its very heart, AI isn't really about programming logic. It's about geometry. It's all about taking data and picturing it as points and arrows, vectors, in some crazy high-dimensional space. If you really want to get AI, you have to stop thinking like a programmer and start thinking like a geometer. Okay, so here's the game plan. We're going to start with AI's hidden language and its most basic building block. Then, we'll map out the playing field, figure out what the ultimate goal is for our data, and see how we can actually engineer the perfect space for it. And finally, we'll see how all this stuff transforms you from just a user into a true architect. All right, first things first, let's break this all the way down to the absolute fundamental piece, the atom of all AI operations. This one thing is what everything else is built on top of. And that atom is called a linear combination. Look, all it means is you take a bunch of vectors, you can think of them as arrows pointing to concepts like royalty or gender, and you just stretch them or shrink them, and then you add them all together. That's it. That one simple move is the foundation for literally everything that comes next. And hey, if you're a software engineer, a little light bulb should be going off right now. This is basically the same thing as a weighted sum in a neural network. When you're training a model, what are you doing? You're just trying to find the perfect weights, those perfect scaling numbers, to mix your inputs together to get the output you want. So if linear combinations are our Lego bricks, what can we actually build? Well, that leads us to the playing field itself, and this field is defined by two huge ideas, span and linear independence. Span is all about reach. It's the collection of every single point you could possibly get to by mixing and matching your vectors. In the world of AI, we call this the expressive power of your data. Think about it. If your problem needs a three-dimensional answer, but your features can only span a flat two-dimensional sheet of paper, your model is dead on arrival. It just can't get there. Now, inside that space, we need to be efficient. And that's where linear independence is key. A set of vectors is independent if every single one adds something new, something unique to the mix. It means no vector is just a rehash of the others. In other words, zero redundancy. And the comparison to software development here is just perfect. On the left, you have linear independence. That's like clean, decoupled code, where every module does its one job perfectly. On the right, that's linear dependence. It's tangled, spaghetti code, it's a redundant mess that just introduces noise and makes your whole system unstable. The source material really nails it with this quote. It says that, from an information theory point of view, linear independence is efficiency. It's about cutting away all the noise to find the essential core structure of your data. Okay, so we want unique, efficient vectors, we get it. But what's the dream? What's the absolute best-case scenario we're shooting for? That, my friends, brings us to the beautiful concept of orthogonality. Orthogonality is the peak form of independence. It means your vectors are perfectly perpendicular to each other, like the x, y, and z axes in 3D space. You know, their dot product is zero, which is just the mathy way of saying they have absolutely nothing in common. A change along one has literally zero effect on any of the others. And this is why that's so incredibly powerful. It creates these clean, separate channels for information to flow. In a language model, this is what lets the model understand the difference between, say, the tense of a verb and the meaning of that verb. They become two completely separate ideas that don't interfere with each other, which is just crucial for clarity. So this idea of perfect orthogonal independence is the goal. But we all know real-world data is, well, it's a mess. It's tangled. So how do we get from that messy reality to this perfect idealized space? Simple. We engineer it. And the tool for the job is called the Gram-Schmidt process. Honestly, the best way to think about this process is just refactoring your data. You're taking this big ball of mud, all these messy, overlapping features, and you're systematically cleaning it up, turning it into a set of clean, modular, and totally independent components. How cool is that? So here's how it works in a nutshell. First, you just pick a vector and say, okay, this is our foundation.
Then you take the next vector and you figure out what part of it is already explained by the first one, like its shadow, and you just throw that shadow away. What's left is completely new, completely independent. You just keep repeating that subtract the shadow trick for every vector, one by one, until the entire space is perfectly squared off.
So what's the big picture here? What does all this get you? Well, when you start to understand these geometric ideas, your whole relationship with AI, it just changes. You're no longer just a user, plugging things into some black box. You now have this incredible geometric toolkit. You use linear combinations to build new concepts, you understand span to know the limits of what's possible, you chase linear independence to be efficient, you aim for orthogonality to get perfect clarity, and you use Gram-Schmidt to build that perfect foundation, even for messy data. And this all leads to this really powerful final idea. When you master this geometric language, you stop being someone you just calls a library function. You become an architect of intelligence itself. You're actually designing the structure of how your model thinks. Look, this isn't just a bunch of abstract math. This is the native language of AI. So the only question left is, now that you speak the language, what are you going to build?